A 50 diameter steel rod support a 9 kilonewton load, that is 9000 Newton load, and in addition is subjected to torsional moment of 100 Newton meter as shown in figure. Determine the maximum tensile and the maximum shear stress. So this force F is not passing through the axis of the shaft. Therefore, you have to shift this force so that you will get one axial load passing through the axis and one bending moment will produce. So let's call this force is equal to F. Let's say this one is the length equal to L, and we want to pass this load to the point A. So from point B we want to shift it to the point A. So whenever the line of action of force has been changed, in that case the force will be shifted to point A will be as it is, and there is no change in the magnitude and direction of the force. So the same force F we can show at point A. So as shown in the figure, the force is shifted from B to A and is same magnitude is equal to F is equal to 9000 Newton. But the additional moment is developed about point A, so that moment we can calculate as moment of F about point A. So we have force is F multiplied by perpendicular distance is L, and this moment is clockwise. So clockwise is moment developed, and this moment is same as equal to 9000 multiplied by distance equal to 28 will be 252,000 will be Newton mm. So you have to show the bending moment here, and this bending moment is clockwise. So this one is the direction of clockwise, and this value of m will be equal to 252,000 will be Newton mm. Because of the moment here, the bending stress will produce. In addition to this, we have a one torque that equal to 100 Newton meter. So we have torque is equal to 100 Newton meter. The diameter D is also given. This diameter D will be equal to 50 mm. So because of the torque, the shear stress is produced. Because of the bending moment, the bending stress will produce, and because of the force F, the axial stress is produced, which is tensile in nature. So you have to first calculate what is the axial stress, the distribution of axial stress. So over the entire cross section, due to the force F, tensile stress is produced, and this stress is uniform everywhere, that is throughout the cross section. And we are interested to know this axial stress. This axial stress will be equal to sigma A, and we have value of sigma A will be equal to force upon area. That will be same as equal to 9000 divided by pi by 4. So 4 will shift in numerator divided by pi into diameter square. We have diameter equal to 50. So we have 50 square. So this stress amount to be 4.58 will be megapascal. In the second case, we'll discuss the effect of the bending moment. Because of a bending moment, we have reaction bending moment will be like this. So this one is going to cancel it. Because of this, the beam AC here, that is a circular shaft here or rod, will going to bend. So approximately the curvature will form like this, and you will get here the shortened member on this side, which is a compressive stress, and this side we have tensile stress. It means that at point P we have tensile stress. Here also at point P we have tensile stress. At point Q we have a compressive stress is negative, but at point Q we have axial positive stress. The distribution of bending stress will be tension at point P, and it's a maximum value, and then the value will go on decreasing. At neutral axis we have bending stress be equal to 0, and on other side, that is at point Q, we have bending stress is negative. So at point P we have positive value of a bending stress, and at point Q we have negative value of a bending stress. So we can calculate here the maximum bending stress will be equal to bending moment multiplied by y divided by I. Maximum bending moment will be plus or minus both value. For positive value you have to select for the point P, and negative value you have to select for point Q. So this will be 252,000 multiplied by y. Y is d by 2. D is equal to 50. So we have 50, and divided by 2. Moment of inertia is pi divided by 64. 64 will come in numerator. Multiplied by diameter to the power 4, 50 to the power 4. So this is plus minus value is 20.53. That will be megapascal. Finally, we will take the effect of the torque, which is 100 Newton meter, and this torque will develop the shear stress on the periphery and is the maximum value. So we can show the shear stress distribution. This will be maximum value for point P. So this will be tau max, and same value is for Q also. That is the maximum value. This is also equal to tau max. In this case, we have tau max will be given as 16 times T divided by pi d cube. That is, we have 16. Torque is equal to 100 multiplied by 10 to the power 3 will be Newton mm divided by pi, and we have diameter equal to 50 cube. So this value will be equal to 4.07. That will be megapascal. Now we can show the stress element at point P and at point Q. So we'll consider here the two sections, that is at point P and point Q. So this one is representing the Q, this one is representing the P. One axial stress is acting in a downward direction for Q. So we'll show here one axial stress, that is a tensile in nature. So we'll show it downward like this. And this value is sigma axial, which is equal to 4.58. Similarly, at point P also the axial stress distribution is remain same. So this value of sigma A is equal to 4.58. Secondly, we will show here the bending stress. The bending stress is downward for P and is upward for Q. So you have to show it upward. This value is sigma B will be equal to 20.53. Whereas for P it will be acting downward, that will be equal to 20.53. So this one is the addition of two stresses. This value is same as sigma B, and this is negative, this is positive, so this value will be less. It means that normal stress wise the P is critically loaded. And finally we will show the shear stress. Shear stress we can show like this. So this value is same as our tau xy, and we have tau xy is equal to 4.07. Same value of the shear stress we can show here also. So tau xy. So as you see from this figure, this net stress acting in the y direction will be less and the stress acting along the y direction is more. It means that this one is a critical point. So this one is a critical state. It means that this bar will fail at point P and not at point Q. So we will design here only for P, and we want to find out here the maximum tensile and the maximum shear stress for P, that is a critical state. As far as the P is considered, the stress acting along the x direction is sigma x, that will be equal to 0. The stress acting along the y direction will be equal to 4.58, that one is a axial stress, plus we have 20.53, that will be the bending stress. Together this value will be equal to 25.11, that will be megapascal. And one shear stress you have to show, that equal to tau xy. So this value is tau xy, and the value of tau xy is 4.07. So in this fashion the state of a stress is developed. Other two stresses we can show like this. So this one is balance state of a stress. To calculate the maximum tensile stress, we will select the positive sign, and we have sigma max equal to sigma x plus sigma y 2 plus under root of sigma x sigma y by 2 whole square plus tau xy square. In this case we have sigma x equal to 0, sigma y is equal to 25.11 and is divided by 2, plus we have under root of sigma x equal to 0 minus sigma y is 25.11. Whole thing is divided by 2 and we have square of it, plus we have tau xy square. Tau xy is 4.07 and we have to make a square of it. So maximum tensile stress will come out to be 25.8, that will be megapascal. And this value itself is a maximum shear stress. That is, under root sign is a maximum shear stress. We have tau max equal to sigma x minus sigma y v2 whole square plus tau xy square is same as under root of 0 minus 25.11 divided by 2 whole square plus 4.07 square. In this case, you will get the value of tau max is equal to 13.8. That will be megapascal. For a given condition, that is, we have given here one cantilever beam, that is a circular shaft, and to the end we have attached a gear whose weight equal to 100 Newton. We want to calculate the maximum shear stress induced in the shaft. The torque acting at the free end is 100 Newton meter, the weight of the gear is 100, and the weight of the shaft is UDL as shown in the figure is 50 Newton per meter. And the diameter of the shaft is given as 45 and the length of the shaft is equal to 750 mm. The torque is acting is equal to 100 Newton meter that will develop the shear stress, and due to the weight and the self weight the bending moment is caused. So we'll convert this diagram into line diagram and we'll calculate the maximum bending moment at the fixed end A. So at point C here the weight is acting downward, so we'll show the weight is equal to W, that equal to 100 Newton, and the total weight here is equal to W into L. So we have total weight will act here, that equal to W into L, that will be same as equal to 50 is Newton meter, and we have length is 0.75 is 37.5 will be Newton. The weight W will act from the point A at a distance equal to total length equal to 750. So we'll call this one as L, and we have L is equal to 0.75 meter. Whereas the UDL will act exactly halfway, so this value will be equal to L1 is L by 2 is 0.375, that will be meter. So this total force WL multiplied by L1 plus W into L will make a bending moment about the point A. Torque is acting at the free end, that is at the gear, that equal to T is equal to 100 Newton meter. So bending moment at A will be maximum is same as equal to W, that is a UDL multiplied by L multiplied by length equal to L1 plus we have weight multiplied by length equal to L. So we have total weight is W multiplied by L. In this case W into L is same as 37.5 multiplied by L1 is equal to 0.375 plus total weight is equal to 100, and we have length is equal to 0.75. The maximum bending moment at point A will be equal to 89.0625, that will be Newton meter. Now because of a bending moment here, the maximum bending moment produced will be equal to 32 times bending moment at A divided by pi dq. We treat that value as a sigma x, and because of a torque we have shear stress is produced, we treat that value is equal to tau xy is equal to 16 t by pi dq. Now only the bending moment and twisting moment are acting on the shaft at point A, and therefore we can calculate here equivalent torque. We have equivalent torque is same as under root of m square plus t square, that is same as ma square plus t square. That is we have under root of 89.0625 and we have square of it plus we have the torque is equal to 100. So we have 100 square. Using the equivalent torque we can calculate the maximum shear stress. So this time we have equivalent torque come out to be 133.91, that will be Newton meter, and this torque is same as equal to pi by 16 multiplied by diameter cube multiplied by maximum shear tau max. So we are not going by conventional formula of tau max as under root of sigma x minus sigma y by 2 whole square plus tau xy. Rather we are calculating the equivalent torque because the shaft is subjected to twisting moment and the bending moment. Now diameter is same as equal to 45, so we have tau max equal to 133.91, that is Newton meter is multiplied by 10 to the power 3. This 16 is multiplied divided by pi and diameter is 45 cube. Solve this, you will get the maximum shear. If you solve this, you will get the maximum shear that equal to tau max is come out to be 7.48. That will be megapascal. Determine the maximum shear stress in megapascal for the shaft of an overhang crank which is subjected to force of 2 kN as shown in figure. So we have given here a circular element of diameter equal to 36, height is equal to 150. On the top surface we have overhang crank. So we have force is equal to 2 kN and is acting at point B. So first job is that you have to shift this force to the center line, that is at point A. So when the force is shifted, the force will be shifted as it is. Already we have done in one case, and this force will develop a torque about the axis, and the torque will be same as equal to force multiplied by length equal to L. That is the length of handle is equal to 300 mm. Call this one is L1, and let's call this as a length of the cylinder is equal to 150. So whenever we are shifting the force from any point and the line of action has to be changed, then you have to follow the two steps. So first step is that the force will remain same as it, no change in the force in the magnitude and direction. So same force you have to show at point A. So at point A you have to shift the force, and this value of the force F will be same as equal to 2 kN. So that will be equal to 2 kN. And we have developed a torque here because the additional moment is produced due to the force F at A. That will be the torque T, and this torque T will be equal to the force F is equal to 2 kN, that is 2000 Newton, and the length L1 equal to 0.3. So in this case we have total torque produced will be equal to 600 Newton meter, and the direction of this torque is anti-clockwise. So this torque you have to show in this plane. So let's represent a torque here. So this one is a torque equal to T, and the diameter of the cylinder is equal to 36 mm. Length of the circular shaft equal to 150 mm. So we'll continue our analysis with the help of this figure. We have one force shown and one torque shown. The length of the shaft is equal to 150 and diameter equal to 36. For simplicity, I will turn this figure by 90 degree. So if you rotate by 90 degree, you will find the force F is acting downward, and we have torque is equal to 600 Newton meter. The shear stress due to the vertical force will neglect here. Only we'll consider here the bending stress and the shear stress. Maximum bending moment will be at point B, and we can calculate the maximum bending moment about the point B. That value will be same as equal to F multiplied by L, and we have value of F equal to 2000 and the length equal to 0.15. So in this case the maximum bending moment will be equal to 300 Newton meter. So this value will treat as same equal to M, and the shear stress due to the force will neglect. In that case the shaft is subjected to one bending moment and one twisting moment at point B. So we can calculate here equivalent torque. We have equivalent torque is equal to under root of T square plus we have M square. That is we have under root of T square will be same as equal to 600 square, and we have M square equal to 300 square. And once we can calculate the equivalent torque, then we have equivalent torque is same as equal to pi by 16 d cube. Then we can calculate value of tau max. So equivalent torque we can replace as pi by 16 into d cube into tau max, and the equivalent value come out to be 670.8 will be Newton meter. From this we can calculate tau max. So we have maximum shear equal to 16 times the torque, which is 670.8, but is Newton meter. So we'll multiply by 10 to the power 3 divided by d cube, and we have diameter equal to 36. So we have 36 cube. I think the pi is left, so we have to divide by pi also. So we get the value of tau max equal to 73.22. This answer will come in megapascal. The video you are watching is from the app, which is the Mohod class app available on Google Store. And in this app, we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.